Welcome back. This is part 2 of a 3-video series on OLS, that is linear regression. The first video, which I encourage you to watch before this if you haven't already, covered the mathematical details of estimating bivariate regression coefficients and how regression relates to variance, covariance, and correlation. In this video, I'll spend some time discussing the assumptions of linear regression, which you may also want to rewatch the earlier video on linear assumptions to help with. I'll also discuss how to interpret results and some alternatives. The final video will discuss extending OLS regression to multivariate models. So to first review the first video, the bivariate regression equation takes the form y equals b0 plus b1 x1. b0 is a constant term that tells us what y will be if x is 0. b1, the regression coefficient, is usually what we're most interested in. For bivariate regression, it's equal to the covariance of x and y divided by the variance of x, or equivalently the sum of cross-product deviations for x and y divided by the sum of squared deviation for x. We can then use this information to directly estimate b0 by rearranging the regression equation, and if we calculate predicted values for y, based on each case's actual x value, we can also estimate the proportion of variance in y that's explained, known as r squared because it's equal to the squared value of the Pearson correlation coefficient r. And that's where we pick up now. So I want you to think for a sec. Stop and think about units in relation to how we estimate regression coefficients. If we start with the formula b1, the coefficient, equals the sum of cross-product deviations of x and y divided by the sum of squares of x, we could expand the top to be the sum of x minus x bar times y minus y bar, and the bottom to x minus x bar times x minus x bar. It would be great if we could divide each case, because then the x minus x bars would cancel out and we'd only have to calculate two values. Instead, we have to add them up first, or else the math doesn't work out. The units, however, will be the same as if we'd done that, since each value in the sum would have the same units. So our coefficients units then are the difference in y minus y bar, per difference in x minus x bar. This is the essential clue to interpreting regression coefficients. b1 denotes the predicted difference or change in y for each unit change in x. If x goes up by 1 unit, the predicted y increases by b1 y units. If x increases by 2, y increases by twice the coefficient. If x decreases by 1, y decreases by the coefficient. And if the coefficient is negative, the math is the same, but the resulting signs are reversed. That is, an increase in x would be associated with a proportional decrease in y. Now notice here, my language carefully refers to associations, not causality. OLS regression with cross-sectional data, that is, data that's all collected together, can't distinguish causal ordering. Usually, though, you're interested in cause and have some kind of a hypothesis about the order, what causes what comes before what. You want to find out if study time affects test scores, for example, or if capital punishment affects crime rates. There are many ways to do that using longitudinal, that is, over time data, or special causal analysis techniques. But unless you're looking at an experimental manipulation, that is, randomized groups given different treatments, all you can usually say from OLS regression is that the two are associated. That is, when one variable is higher in a certain way or lower in a certain way, we expect on average the other variable, the y variable, to have some kind of proportional change related to that coefficient. The most common way to interpret a regression coefficient then is something like a unit increase in x is associated with a b1 unit increase or decrease in y. If you're more interested in predicting y than modeling a relationship, you might put it a little differently. You might say the predicted value of y is b1 units higher or lower from each additional point or unit of x. That still leaves us with the constant uninterpreted, though. Mathematically, the constant, the b0 term, is the predicted value of y when x is 0. The one exception is if all variables are mean-centered. Then the constant will always equal 0, so it can be ignored. Sometimes 0 is a meaningful value for x. So if we're researching the relationship between study time and test scores like we looked at in the last video, 0 is unfortunately a common x value for many students, although I'm sure none of you. What if your independent variable is pulse rate? It has a natural 0, but it's difficult to get people's consent to take a survey when their pulse rate is 0 because they're either dead or unconscious. So in the first case, study time and test score, we can interpret the constant fairly easily. We can say a student who studies 0 minutes is predicted to score 50 points on the test, and each minute of study is associated with an increase of half a point in score. If B1 is small, a quarter, or a half, it may make sense to turn around the end of the sentence and say a student who studies 0 minutes is predicted to score 50 points, and every 2 minutes of study is associated with a 1-point increase in score. The two are equivalent, but the second's easier to understand. Now, in the second case I brought up before, not the test scores now, but the pulse rate, and say positive affect, feeling good. It's common to just not include the constant when you interpret it verbally. It needs to be there for the math. But if B1 is 0.10, we might say a 10 beat per minute increase in heart rate is associated with a 1 unit increase in positive affect, and leave out the constant when interpreting because that 0 doesn't necessarily make a lot of sense or affect how we interpret it. Of course, that doesn't give us permission to ignore the constant in our equations or our graphs, but it reflects the relatively limited substantive importance the constant conveys in and of itself. Now that we know how to find and interpret coefficients and constants, we need to take one more step back. Think about when we shouldn't interpret them, not just because they're substantively confusing, like above, but because OLS regression is not a valid method for estimating them. As far as the coefficients, and thus the constants, are concerned, there are 4 assumptions that need to be met for bivariate OLS regression. The first is the assumption of non-zero variance on both variables. You shouldn't have a problem with this because you wouldn't get this far if either variable didn't vary. It would be impossible to estimate coefficients. The computer would tell you, no, I can't do it. Or if you tried to do it by hand, you'd find the deviances were all 0 for one of them. So the covariance would be 0. Or if it was the x that didn't vary, the covariance would be undefined. The other 3, though, were not quite so easy to spot, as you can easily estimate coefficients despite violating them. So it's important to watch out for them. The second of the 4 is variable types. Linear regression assumes the dependent variable is continuous, it has no jumps, it's unbounded, meaning data cover the full range of possible y. It doesn't necessarily mean y has to go on forever either way, but if you have a scale that goes from 1 to 10 on positive affect, you assume that you have at least some cases that have all of those values. And y needs to be interval level, not categorical, and it needs to have equidistant units. So for example, if you had a binary dependent variable, you'd be estimating a line to predict an infinite number of possible values when actually there are only 2 possible values, 0 and 1. If your dependent variable doesn't meet these qualifications or approximate them, your coefficients and standard errors will be biased. We want to avoid that if at all possible. Now, in addition to the restrictions on dependent variables, independent variables are also restricted, but not so much. In addition to allowing interval level variables, independent variables can also be binary dummy variables, that is, 0 or 1. This changes the interpretation, though. In this case, the B1, the coefficient, represents the unit change in y associated with being in category 1 instead of category 0. Interpreting anything per change in x makes no sense when there's only 2 categories and they're nominal, not a large scale of possible values. This still excludes multi-category independent variables, unless they're dummy-coded and used in a multivariate model, like we'll discuss in the next video, and it requires the researcher to make a decision on ordinal level variables. Do I treat them as categorical nominal variables, or do I treat them as interval variables? The third assumption is that estimates may not be valid if external variables are correlated with both x and y and left out of the equation. Because any association or non-association you see in your results, that is the size and the significance of the coefficients, may come from a spurious cause or an intervening mechanism. In practice, this assumption needs to be evaluated based on theory and past research or using multiple nested models, since there's no way to categorically rule out all other variables. There could always be something you're missing. Finally, the relationship between x and y must be linear or approximately linear. For two variables, it should be easy enough to look at a scatter plot before you run a model and check that it looks generally linear or not. For example, it could look curvilinear, that is, it could follow a parabolic curve. In that case, your linear regression coefficients are going to be far off. You can still estimate a linear model for those nonlinear relationships, but you're likely to find a small or non-existent result, small coefficients, high standard errors, if it's misspecified. On one exam, I asked the class to write down the time they finished the exam, then I converted those into a score of how long they spent on the test in minutes, used that to predict their test scores. The linear model we estimated had an R-squared of 0.02, that is, only 2% of the variance in test scores was explained by the time. But correcting the specification to a curvilinear model increased the R-squared to nearly 0.5, that is half the variance explained, and produced a curve much closer to the shape of the scatter plot. There are many other forms of nonlinearity. There are other forms of nonlinearity too. There can be curves with multiple inflections or waves. There can be discontinuous functions where y seems to jump at specific values of x, and so on. In reality, violating the variable type assumptions would also produce nonlinearity, I should note, because those very violations would, for example, if the y variable was binary, you can't have a linear relationship because the scatter plot is just two lines of points across. So really, the three testable linear assumptions that affect bivariate coefficients can all be assessed with a scatter plot. There are other linear assumptions that don't bias coefficient estimates, but do make them inefficient, that is, make larger differences between samples, and bias the standard errors upward, affecting our significance test and our confidence intervals. Now, these can only be evaluated after estimating the equation, and they include the assumption of independent errors, the assumption of homoscedasticity, the assumption of normally distributed residuals, and normally distributed sample parameters. Coefficients should be expressed with less certainty if their estimates are inefficient, while significance values and confidence intervals should not be used when either type of violation is present to more than a small degree, unless you're correcting for it using a robust estimation technique. For more information on these assumptions and how to detect them, review the video on linear assumptions. Now, many alternatives are available, I should say, that have been designed specifically to deal with data that violate these linear assumptions. They generally do one of three things. They adapt the data to fit linear assumptions better, they adapt the model to loosen linear assumptions, or they adapt the estimation to adjust for violations. Data can be transformed or trimmed in the first case, but caution should be exercised whenever valid data are being modified. Other models, the second case, include logistic regression, which allows for binary dependent variables, and many other models we won't cover in this course that are designed to deal with ordinal variables, count variables, nominal variables, correlated errors, nonlinearity, and other violations. Bootstrapped estimates and Bayesian estimates of standard errors are examples of this, the third type, the adjusting estimation. They produce more robust estimates that are less influenced by these violations without changing the data or the model itself. Now, which, if any, adjustments should be made is a decision that you'll have to make that will be driven by both theory and careful examination of the data. So to summarize this video from end to beginning now in reverse, so that you can sort of think back over the whole scope, which is a fairly broad scope in this video. First, there are adjustments that can be made to data, to models, and to estimation in case of violations of linearity assumptions. Next, the most important assumptions for bivariate OLS regression are linearity and variable type because they bias coefficient estimates. Other assumptions are important for obtaining stable estimates and evaluating significance of confidence intervals. Next, constant that b0 is mathematically what y is predicted to be when x is 0, but it may or may not have substantive meaning depending on the possible values of x. The regression coefficient, the b1, is the change in predicted y for each 1 point increase in x, or for moving from 0 to 1 on a binary independent variable. 6. Substantive interpretations can take the form of a 1 unit increase in x is associated with a b1 unit change in y, or the form the predicted value of y changes by b1 for every 1 unit of x. Your choice depends on whether you're trying to explain or predict as your primary goal. And finally, OLS regression provides evidence of association, providing assumptions are met, but never of causality. Hopefully that helps you understand and interpret regression at least a little better. So thanks for watching, have a great day, and don't forget to watch the third video.